Now that we are familiar with diodes, transistors and thyristors, we will apply these components as building blocks in many types of converters. We will start with DC-DC converters, which is the topic of the next few videos. In this video, we will introduce the first group of converters, the DC-DC converters, which are able to regulate DC power between different voltages. We will then briefly discuss examples of DC-DC converters, the step-down or buck converter. We will examine its circuit diagram and look at its governing equations. DC-DC converters are switch mode converters because they operate by opening and closing switches. Power transistors are used as switches. In addition, capacitors and inductors are used as energy storage devices. By cleverly controlling the switching instances, the flow of energy between the input and the output is manipulated, making it possible to accurately control the voltage at the output. These DC converters can be found everywhere. To name a few examples: smartphones, computers, electric vehicle chargers. We even find DC converters in solar panels. In the coming lectures, we will discuss three different types of DC-DC converters. The buck converter, which steps down the output voltage. The boost converter, which steps up the voltage so that the output voltage is always larger than the input. And finally, the flyback converter, which is used when electric isolation between the input and output is needed. First, we will start with the buck, or the step-down converter. As the name suggests, the step-down converter steps the source voltage down to a lower voltage at the output. Here we can see the circuit diagram of the converter. This is the transistor, which is used to actively regulate the output voltage. The transistor is operated as a switch that connects the input voltage source to the circuit. The ratio of the on-off time of the transistor is varied, making it possible to regulate voltage. This we will discuss in the next video. Here we have an inductor and a capacitor which store and release energy as the transistor is switched on and off. Together, L and C function as a low-pass filter, smoothing out the current and voltage supplied to the load resistor. When the transistor is turned on, we can consider it as a switch that is closed. The current flows through the switch, through the inductor, through the parallel connected resistor and capacitor, back to the source. When the switch is open, no current can flow through it. Therefore, an alternative path for the inductor current is needed. The path is provided by the diode. During the time when the diode conducts, the voltage polarity across the inductor is reversed. The current now returns through the diode, completing the loop around the inductor and capacitor and resistor. By varying the duration of the on state of the switch, we can control the average voltage across the load. Let us now write down the equations to describe the output current and voltage. So this is the equivalent circuit when the switch is closed and conducting current. We can calculate the current and voltage using Kirchhoff's laws. Using circuit theory principles, we derive these differential equations for current and voltage. Note that previously we have analyzed circuits with only one energy storage element, either an inductor or a capacitor. In this circuit, we have both. The buck converter is a second order circuit. If the switch is open, we have this equivalent circuit where the diode is conducting the current. Because the circuit is different, it changed, we need to derive a second different set of differential equations to describe the current and voltage. The approach using more than one set of differential equations is known as state space analysis. Note that there is a third possible state. If neither the switch nor the diode is conducting during an interval, the switch is said to be operating in the discontinuous conduction mode, or in short, DCM. For now, we will only consider circuits which are always conducting current, which is described as continuous conduction mode, or CCM. In a second-order circuit, it is often not possible to derive the exact analytic solution for these differential equations. Usually, the circuit is solved computationally with software that simulates the current and voltage in these circuits, so we don't have to do it ourselves. However, it is possible to do an approximate analysis of the circuit, which can give us a good estimation of the current and voltages in a step-down converter. This will be the topic of our next video. To recap, in this video we introduced DC-DC converters and discussed the first member of this family, the step-down or buck converter. We derived the exact equations for these circuits. In the next video, we will introduce an approximate analysis. Thank you for watching.